Welcome back. In the second part of this section, we're going to talk about a related theorem to one we've seen earlier on, the mean value theorem. Before, we saw the mean value theorem for differentiation, which told us that if we had a nice differentiable function and we were looking at calculating the average rate of change over some interval from a to b, that would be the same thing as the derivative at some point c where c is inside of our interval from a to b, that we were guaranteed that at some point the actual rate of change, the instantaneous rate of change, would be the same as the average rate of change. And the fact that we were talking about an average was the reason it's called the mean value theorem. Remember, a mean is just another name for an average. This one, though, is related to integrals. And so for this, we have a function. We don't care if it's differentiable, we care if it's integrable, and it is because it's continuous from a to b. So we're told if that's the case, if you have an integrable function, then that definite integral will be equal to b minus a times f of c, where c is some number inside of our interval. So again, it's guaranteeing that there's a point in our function that will do something nice for us. And in this case, that the value of f of c times b minus a will be equal to what our definite integral is. Right now, this doesn't really look like it's talking about an average of anything, but of course, if you thought about it, we could rephrase this equation so that we say actually that f of c is 1 over b minus a times that definite integral. And that looks a little bit more like an average. So if you're remembering from any stats that you might have done in the past, when you're finding the average of a bunch of numbers, we're adding them up and then dividing by how many numbers we've got. And it kind of looks like we're doing some sort of averaging here. We have our definite integral, which we remember that has its origin story in a Riemann sum. So we're adding things up, and now we're dividing by the length of our interval. So it kind of feels that this should be some sort of an average. And in fact, it is. If we've got a function that's integrable, and if our function is continuous, then yes, it is, then that expression that we had, that 1 over b minus a times our definite integral, that's the average value of our function. That is keeping track of all the function values that we had over that interval, averaging them out. That would be that definite integral divided by b minus a. So in other words, what the mean value theorem is really telling us is if you have a nice continuous function, then somewhere you will have the function actually taking on that average value. So for example, if I were thinking about keeping track of some object that is moving at a different variety of velocities, and if I were to keep track of its average velocity, well, somewhere over that interval, it must achieve that average velocity. So if you were traveling around and your average speed that you were traveling around at was 30 kilometers an hour, then provided that the function that describes your velocity is continuous, then that means at some point you must have actually had a velocity of 30 kilometers an hour. In other words, at some point there will be the average value actually getting attained. So let's see this in action. So first off, we've got this function, and it's defined on that interval from 1 to 2. And f of x is a polynomial, so definitely it is continuous on that interval, but in fact it's continuous on every interval. So I can say that since f is continuous on that interval from 1 to 2, then the mean value theorem applies. Because remember, the only thing that we required for the mean value theorem for integrals was that our function was continuous on a closed interval, and f is a polynomial, it's continuous on that closed interval, so we're good to go. So now, if I wanted to find that average value from 1 to 2, then that would be the integral from 1 to 2 of f multiplied by 1 over the difference between the endpoints, 1 over 2 minus 1. Conveniently enough, of course, 1 over 2 minus 1 is the same thing as 1 over 1, which is just 1. So really the average value of f will just be the definite integral of 6x squared plus 4x minus 1. And we know how to do that, so I'll just evaluate and integrate and evaluate. So antiderivative of 6x cubed would be 6x squared would be 2x cubed. For 4x, it's 2x squared. And for 1, it's x. And we'll evaluate that between 1 and 2. When we evaluate it at 2, we'll have 2 times 2 cubed plus 2 times 2 squared minus 2, which is 22. And when we evaluate it at 1, we'll have 2 times 1 plus 2 times 1 minus 1, which is 3. So it looks like for f, the average value that it achieves over that interval from 1 to 2 is 19. So what the mean value theorem is telling us is that f of x should be equal to 19 at some point in that interval. It might be equal to 19 elsewhere. It might be equal to 19 in a bunch of places, but what the mean value theorem is guaranteeing for us is somewhere in the interval that we're interested in, it will take on that value. So somewhere f of x should be equal to 19, and that somewhere should be between 1 and 2. So let's find that. Now, we want to find the c in that interval where f of c is equal to our average value. So we want f of x to be equal to our average value, which we just found, which was 19. So in other words, we're looking for 6x squared plus 4x minus 1 to be equal to 19. Or 6x squared plus 4x minus 20 to be equal to 0. You could try to make this look a little bit nicer for yourself, dividing everybody by 2, but I mean, it's still not going to factor. So I guess at that point you would give up and do quadratic formula like I'm doing right here. Negative b plus minus root of b squared minus 4ac over 2a. So negative 2 plus or minus the root of 124 over 6. Now, if we run that through our calculators, we get two values for x. One of them is negative 2.189, and the other one is about 1.5226. And there we go. That's the value c that we were looking for. C that we were looking for was going to be inside of our interval from 1 to 2. We were guaranteed that that value existed by the mean value theorem, and lo and behold, we have found it. So the value of c that we were looking for is about 1.5226. That's the place where f of c is equal to our average value of f on that interval. Okay, let's do another one just for fun. We've got ourselves standing at the top of a very tall building. It's 490 meters tall. I'm just going to release the coin, so I'm not throwing it. So when I release it, that means initially it's not going to have any velocity. So I'll write that down. The initial velocity for this coin is 0. I'm not throwing it up in the air. I'm not throwing it downward. I'm just letting it go. I also know the initial position, so I guess I should make a note of that. The initial position is 490. And so now let's find ourselves our functions. For the velocity function, we know that velocity is the integral of acceleration. And I know acceleration due to gravity is downward at 9.8 meters per second squared. So I need to integrate negative 9.8 with respect to t, and I'd get negative 9.8 t plus a constant. Now, if I go ahead and use my initial value, if I put in 0 for velocity and 0 for time, I'll find that my constant c1 must be 0. So that means my actual velocity equation should be just negative 9.8 t plus no constant at all. So that's part of our work finished for us. I'll just underline that so I remember to come back to it. And now we want position, and position should be the integral of velocity and I'll get negative 9.8 t squared over 2, which is the same thing as negative 4.9 t squared, plus another constant. And then same sort of thing that I would do here, using my initial condition of s of 0 is 490. So if I put in 490 for s and 0 for time, I'll solve and I'll be able to find that the second constant is 490. So I'll find that actually my equation for position should be s of t is negative 4.9 t squared plus 490. And so now we're good to go. We can answer whatever questions we have about positions or velocity because we've got both of those functions. And so the first question that I want to address is in part B. When does my coin hit the ground? Or in other words, when is the position of my coin equal to 0? So if I try to solve for time, I'm going to find that t squared is 100, or that t is plus or minus the root of 100. And of course, the plus or minus part is going to be giving us two solutions, 10 and negative 10, but we're going to reject one of those. We're going to reject time being 10 negative because time needs to be greater than or equal to 0. And so I'll say for my conclusion then, the coin hits the ground in 10 seconds. So if I'm just standing at the top of this 490 meter building and I let the coin go, 10 seconds later, the coin should hit the ground. So now the question that we have for ourselves is, what's the average velocity for this coin over its little journey? So if I'm looking for the average velocity, then I'm going to be looking at the definite integral of the velocity function, which was negative 9.8 t. And I'll be doing it over this little journey from time equals 0 to time equals 10. And since it's the average velocity, that should be 1 over 10 minus 0, or 1/10. So now I just have a little bit of calculations to do here. I just need to find an antiderivative of negative 9.8 t, which I know what that is. That's negative 4.9 t squared. And I need to evaluate that between t being 0 and t being 10. So when I evaluate that at 10, I'll have negative 490, and when I evaluate it at 0, I have 0, so I have 1/10 times 490, which is negative 49. So my average velocity is 49 meters per second, and that's meters per second traveling downward. If you wanted to, you can convert that into kilometers per hour. So if you're just curious how fast that is in terms of kilometers per hour, negative 49 meters per second, you know that there are 60 seconds in every minute, and 60 minutes in every hour. And as far as the meters go, we know that there is, in 1 kilometer, 1,000 meters. So meters and meters cancel, minutes and minutes cancel, seconds and seconds cancel, and we're left with something that's in terms of kilometers per hour. And in terms of kilometers per hour, it would be negative 49 times 60 divided by 1,000, or negative 176.4 kilometers per hour. That's how fast our coin is zipping down to the earth on average. In fact, it's going a lot faster than that when it actually hits the ground. So now the thing that we want to address, though, that was just a fun little aside to know about coins, but we want to now think about how does this apply, or how does the mean value theorem for integrals, rather, how does that apply here? We know that our velocity function is an integrable function. It's continuous. And so that means that the average value for our velocity should be achieved at some point between 0 and 10. So in other words, I know by the mean value theorem that I should have my velocity function should be equal to its average velocity somewhere on that interval from 0 to 10. And so now let's figure out, when is our velocity happening to be negative 49? Well, our velocity function was negative 9.8 t. And we're solving for where is that equal to negative 49. And when I solve for this, I find that t is 5. So at 5 seconds, the coin achieves the average velocity. Okay, so just one little last thing to mention before we finish this this video off, and that's just sort of a connection again between the two kinds of integrals. We have our indefinite integral, which is always going to be some sort of family of functions. So if I have a f of x dx that's I'm looking at integrating, that's going to be some sort of function of x. If I look at a definite integral, integrating f of x dx from a to b, if a and b are both numbers, then my definite integral is going to be a number. However, you don't necessarily have to have numbers for your limits of integration. You could have x being one of the limits of integration, or a variable, or some function of that variable. So for example, suppose we had f of t dt and we were integrating it from a to x. If capital F, was an antiderivative, the fundamental theorem of calculus part 1 tells you would just evaluate at the top limit minus evaluate at the bottom limit. So we would have capital F of x minus capital F of a. Since a is a number, f of a should be a number, but if x is a variable, not a number, then f of x, capital F of x, would be some sort of function. So it's possible, if we're talking about a definite integral, that it may not necessarily be something numerical.